Hello ladies and gentlemen, and welcome to our video on acceleration. This is actually section 2 in chapter 2. We talked about what happens when you move at a constant velocity. Now we want to look at cases where we're not moving at a constant velocity, and that's what we're going to get into with acceleration here. So, before we begin, let's actually look at what we need to know. Let's look at our essential questions here. So the first thing we want to figure out is, how is acceleration related to an object's velocity? We want to know what's the relationship between acceleration and velocity, and how they fit together. Second, we want to know what does it mean when the sign of the acceleration is opposite the sign of the velocity, and what happens when they are the same. And then finally, we want to know, how does the acceleration affect the displacement of an object compared to an object moving at a constant velocity. So with constant velocity, we talked about how objects are continually putting out the same distance each time. How's acceleration change that? So, to begin, we're going to pose a simple question here. Let's say you're driving your car and you have a velocity of 55 miles per hour north. Again, we need that direction component in there. So we want to know, how can you change your velocity? So just think about that for a second. If you're going 55 miles per hour north, how can you actually change your velocity? Well, there's really three things you can do. You can step on the gas pedal, which is going to speed you up. You can step on the brake pedal, that's going to slow you down. And you can turn the steering wheel, in which case that will change your direction. All three up is going to increase your velocity by increasing the magnitude. It's going to increase your speed. Slowing down is actually going to decrease your speed, thus decreasing your velocity. And then turning the steering wheel, you have the same speed ideally, but you're actually changing your direction. And since direction is one of the key components of velocity, that's changing your velocity. Well, all three of these actions are examples of what we call acceleration. And I'm sure it's a word you've heard of before. But we're going to actually set a set definition to it, and that definition is this. Acceleration is a rate of change of velocity with respect to time. We're looking at how velocity changes over time. Are we speeding up, slowing down, changing direction? It could be a combination of things. So that's the key question we're asking there. How does an object's velocity change over time? Is it a large change, in which case we're going to be speeding up a lot, or it could even be something very, very small, but it's still changing over time. And the second key point there is, you can accelerate if your speed, direction, or both actually change. It could be one, it could be both. If you're driving on the highway, just for instance, on a road that points north and you hit the brakes, you're just changing your speed. If you're going around a turn, you could be changing your direction. You could even speed up and change your direction. So it could be a combination of things. And the third key point here with this is, if the acceleration is larger, it's going to be a larger change in velocity. If you really step on the gas pedal, you have a great acceleration, and as a result, your velocity is going to change a lot more rapidly. Whereas if you just kind of slightly step down, it'll increase, but it's going to be a very gradual change. So that's what we mean when we talk about acceleration. Acceleration is a change in velocity with respect to time. So with that, we can kind of take the same idea we did with velocity in terms of looking at just an average and apply it now to this acceleration idea. With average velocity, we said that we can find the average velocity by taking the change in position, which we call displacement, and divided it by the time. Well, acceleration is kind of the same idea. Average acceleration is our change in velocity divided by the time interval during which the change occurred. So our general equation is going to look like, it's going to be average acceleration equals our change in velocity over our change in time. So equation-wise, we have kind of two forms. We're going to have one that's the formal definition and one that's the kind of shorthand version. So if you look there where it says equation, we have A average, A stands for acceleration, is delta V over delta T. Remember, delta represents change in. So we're really saying the change in V, change in velocity, over the change in time. So change in velocity is going to be our final velocity, Vf, minus our initial velocity, Vi, over our change in time, Tf, final moment of time, minus Ti, the initial moment of time. We can just kind of generalize that and just say the average acceleration, A, is final velocity minus initial velocity over the time. And that's going to be the average acceleration equation we use the most, probably, in terms of the general format. We're actually going to learn in class a couple other acceleration equations we can use to find different things. Displacement, we could find the acceleration, we can find time. All sorts of things we could figure out. Initial and final velocities. This is the general equation, though, and we can actually get to a lot of places with just this. So, with that said, let's take a look at the units on this, because the units are a little tricky with acceleration. It is velocity over time. So, because of that, with velocity, we know velocities in meters per second, kilometers per hour, miles per hour, all sorts of units like that, and we know times in seconds. So we actually have a rate, a fraction, in another fraction. So we can have, as you can see there, meters per second over seconds, which, if you know your fraction rules, actually ends up being meters per second squared. And that's a unit that shows up a lot in what we're going to be doing. Meters per second squared, also known as meters per second, is a unit of acceleration. It's a velocity unit, that meters per second. And what this identifies is how our velocity changes over time. If you think about it, meters per second. So we have our velocity changing some amount of meters per second every second. You can see the example there at the bottom. 1 meter per second squared, or 1 meter per second, means that the velocity will actually change by 1 meter per second every second. That's what the units of acceleration tell us. It tells us the speed component, and it tells us the time component. Alright, we'll look at the units a lot more in class. It is something you want to be aware of, be able to look at and say, oh, I know what that means. So just keep that in mind. Now, another important part with acceleration is the sign. Which way is it accelerating compared to its velocity? Well, when the acceleration sign matches the velocity sign, then it's accelerating, it's speeding up. Take a look at this airplane here. You can see there at the beginning, it starts at rest, but its acceleration is 9 kilometers per hour per second. So every second, it's going to increase its velocity by 9 kilometers per hour. So after 1 second, it's moving at 9 kilometers per hour. After 2 seconds, it's moving at 18 kilometers per hour. But all of those in the positive direction. So here, our velocity and our acceleration are matching signs, which means it's going to be speeding up in that direction. Alright, so that's one thing we can observe. When acceleration and velocity have matching signs, when they're in the same direction, it's going to be speeding up. If they're in the opposite direction, on the other hand, that's when we're actually decelerating, we're slowing down. So here you can see this little dragster. Again, at the beginning, we're going to say it's moving at 28 meters per second. That V0 is just another way of saying initial velocity. So it starts off at 28 meters per second. After 1 second, it actually drops to 23 meters per second. Why? If you take a look, that yellow arrow there, the acceleration is negative 5 meters per second squared. Every second, the velocity is going to decrease by 5 meters per second. So we go from 28 to 23 in the first second. In the next second, we're going to go from 23 to 18. So in this case, we have a positive velocity, but a negative acceleration. And what's the result? It actually slows down. Its velocity is decreasing. So you want to know how sign interacts with the velocity, and this table actually sums it up very well. If you're speeding up, you can have a positive velocity and a positive acceleration, or a negative velocity and a negative acceleration. Again, it's key that these signs match if it's going to be speeding up. If it's positive, it's speeding up in the positive direction. If it's negative, it's speeding up in the negative direction. On the other hand, if the signs are opposite each other, that's when it's going to slow down. You can see there in the third row, we have a positive velocity but a negative acceleration. That's going to slow down. The next row is negative velocity, positive acceleration. So in that case, it could be something to the effect of you're traveling west, but your acceleration's to the east. You're going to be slowing down. Now, if you have a positive or negative velocity and there's no acceleration, you're moving with a constant velocity. You're not accelerating at all, so it's just going to stay the same. On the other hand, if your velocity is 0, but you have an acceleration either positive or negative, you're actually going to be speeding up. It's just going to be in whatever direction the acceleration is. If you start at 0 and hit the gas pedal, you have a positive acceleration in whatever direction you're facing, so you're going to speed up. So it is possible to have a velocity of 0, but a non-zero acceleration. And if both things are 0, if you have a 0 velocity and a 0 acceleration, you're not going anywhere. You're going to stay at rest until something changes. So these signs are very important. You want to be able to look at the signs, how the sign of the acceleration and the sign of the velocity compare, because that's going to tell you what's going on in terms of its velocity and its behavior, whether it's speeding up, slowing down, or moving with a constant velocity. Okay, so that is a key thing. This is a table that will be very handy, so you would want to write this down, definitely. Now, we covered that. Let's take a look at how distances are covered, more specifically displacements. So what we've been dealing with is constant motion. The idea that we're moving at a constant velocity, there's no acceleration at all, so as a result, each second we're covering a constant displacement. We're going a common distance. So you can see here those yellow circles on the page, that kind of indicates that, let's say every second there's like a little snapshot. Notice that they're evenly spaced. That's what happens with constant motion. It's going to be traveling the same distance each second. And if we look at the data table here we have, let's take an example of, let's just say an object's moving with a velocity of 5 meters per second in the positive direction with no acceleration. Well, that means each second, its initial velocity and final velocity are 5, so its average velocity is 5. And we know from our equations that if we take our average velocity times the time, that'll tell us our displacement. So each second, we're going to be just having a displacement of 5 meters. That doesn't change. So with constant motion, displacement stays the same the whole time. In terms of each second, you're covering the same displacement. Acceleration, on the other hand, is completely different. Because we're changing our velocity, it's actually going to cover different displacements in a period of time. And as a result, you get something that looks like this. You can see the yellow circles. Again, let's just say it's taking a snapshot every second. Notice that distance increases. Now, in this case, we're assuming that the velocity is to the right and the acceleration is to the right. It's going to be speeding up. So let's take a look at that. If we take a look at our example here, it says the object starts at rest and accelerates at a rate of 2 meters per second squared. So every second, its velocity is going to increase by 2. So in that first time period, we start at 0, but we're going to end that time period at 2 meters per second. So from 0 to 2, the average velocity is 1 meter per second. And again, average velocity times time. Hey, we traveled 1 meter of displacement. From 1 to 2 seconds, we would now start at 2 meters per second. Add in our acceleration, we end at 4. That means our average velocity is 3 meters per second, and now we travel 3 meters. So notice from 0 to 1 seconds, that displacement is less than from 1 to 2, because we start off moving faster in that 1 to 2 second time period. From 2 to 3, we start at 4 and at 6, so our average velocity is 5, displacement's 5, and you can see the same pattern emerge from 3 to 4, from 4 to 5. The initial velocity is different for each time period, the final velocity is different, so our average velocity actually slowly increases, and as a result, we're actually going to cover more displacement. So that's the big difference. With acceleration, the displacements are not constant. Each second, it's going to change because the velocity is changing. Okay? That's something we'll look at more when we get to analyzing some motion graphs. You can actually see this more drastically as opposed to just looking at a data table. But you do want to be aware that for accelerated motion, the displacements are not the same. It's not like constant motion, constant velocity, where it's all the same every time. So, with all that said, let's take a look at some kind of think of questions in terms of checking your understanding. So, here's the first one. If a baseball has a 0 velocity at some instant, is the acceleration necessarily 0? Well, no, it isn't. We just know at that point in time it's 0. It could be starting at rest and then somebody throws it. It could be moving and then somebody caught it. It could be any of those cases. We don't know anything about how its velocity is changing. We just know what its velocity is at a certain point. So as a result, we cannot safely say that the acceleration is 0. We just know at that point the velocity of the baseball is 0. So that is something to be careful of. You can have 0 velocity. That's nothing special. That just means it for a moment of time it's at rest. But then if it's accelerating, it can actually change its motion and as a result move. So just be aware of that. All right. Second, check your understanding question. If a passenger train is traveling on a straight track with a negative velocity and a positive acceleration, is it speeding up or slowing down? So this is a question related to signs. So we have a negative velocity and a positive acceleration. So is that speeding up, slowing down, or not at all? Is it not changing at all? Well, if you paid attention, you should know that if they have different signs, we are slowing down. In this case, the velocity is negative, so it's traveling, let's just say, west. Positive acceleration, so it's actually accelerating east. It wants to move east. So as a result, it's going to slow down. It could eventually reach 0, and then if it's continuing to have a positive acceleration, it'll start speeding up in the opposite direction. Alright? Third check your understanding question. Two cars are moving on a straight section of highway. The acceleration of the first car is greater than the acceleration of the second car, and both accelerations have the same direction. Which of those statements is true? Well, if you think about it, which one of those is right? It actually turns out to be option C. In that same time interval, the change in velocity for the first car is greater than that of the second. And that just goes back to the meaning of acceleration. Acceleration is change in velocity over time. If the first car has a greater acceleration than the other, then it's going to have a greater change in velocity in that same period of time. So as a result, D would not make sense. D says the second car has a greater change in velocity. That makes no sense if the first car has the greater acceleration. And A and B aren't necessarily true. You could have cases where the second car is actually traveling faster than the first car, but the first car has greater acceleration. So we have to be careful. Acceleration is a little bit tricky. You have to be very careful in terms of looking at it's the change in velocity. It doesn't tell us really anything about the velocity at a specific point, at least with what we have right now. So keep those things in mind as we move into this section of our unit here. So, to kind of wrap up, let's revisit our questions. At the start we said we want to know, how is acceleration related to an object's velocity? Acceleration is the change in velocity over a change in time. So there's a direct relationship there. What does it mean when the sign of the acceleration is opposite the sign of the velocity? That just means it's slowing down. If the signs are the same, it's speeding up. If the signs are opposite, it's slowing down. And third, how does acceleration affect the displacement of an object compared to an object moving at constant velocity? Well, the key thing is, if it's accelerating, the displacements are not constant. It will travel a different displacement each period of time because it's accelerating, because its velocities change instead of remaining the same. So, those are notes for acceleration. We will talk more about this in class. We'll do a lot more with it in class, and I will see you then.